In pressure conduits, fluid is flowing under pressure from one end to the other. It is different to open channels. One of the key concepts in pressured flow is that of the hydraulic radius. If you remember, the pipe connecting the two tanks in the Bernoulli's equation problems that we saw in the previous recording is an example of a pressure conduit. The hydraulic radius has a dimension of length. The wetted perimeter is the length of the interface between the fluid and the pipe or channel. The hydraulic radius is an important characteristic of a pipe or channel. Another important parameter is the hydraulic diameter, which is equal to 4 times the hydraulic radius. The hydraulic radius can be calculated from equation 16.12 of SERM Here we see table 17.3 of SERM, which shows that you can calculate the hydraulic diameter for different channels, as you see on this. Here we see table 19.2 of SERM, which we can see how we can calculate the hydraulic radius for different channel geometries. For pressure conduit applications, please note this table provides you with a specific formula to calculate the hydraulic radius for a circular channel or a circular cross-section if it's not flowing full. Here we see Appendix 16A from SERM. As you can see here, you can calculate the wetted perimeter and the hydraulic radius based on different ratios between the depth of the flow in a circular pipe and the diameter of the pipe. So we just saw a few different parts within SERM that we can use to calculate the hydraulic radius. Please make note of those sections of SERM. You may want to tap them for use while you practice problems for the PE exam, and you may be using them during the breath portion of the PE exam. The hydraulic radius is a simple concept. It's the area in flow divided over the wetted perimeter. The wetted perimeter is one of my favorite concepts within hydraulics because its simple name almost describes as in a picture of what it means. The wetted perimeter is simply the periphery of the channel that is wet. So in a pipe that is flowing full, if we solve for the geometrical equations, the wetted perimeter, the hydraulic radius is going to be the diameter of the pipe divided over 4. And that is if the pipe is flowing full. Another key concept in pressure conduit analysis is that of the Reynolds number. Inertial force is related to the mass of flow, while viscous force is related to the viscosity of flowing fluids. The Reynolds number is a dimensional number that is simply the ratio between inertial forces and viscous forces. Inertial forces are proportional to the flow diameter, velocity, and density of the fluid, as we see in the upper part of the Reynolds equation. Viscosity is defined as a fluid's resistance to flow under the application of external forces. For a further discussion on viscosity, I will recommend you to review section 15.9 of SERM. The Reynolds number is used in pipe flow for calculating head loss due to friction. This head loss results in a decrease in the energy in the system due to friction. One of the key things about SERM is that the variables used within each chapter are defined at the beginning, at the first page of each chapter within SERM. So you can use that. One of the key things that we can infer from a Reynolds number is whether a flow is flowing under a laminar condition or a turbulent condition. Laminar flow occurs when the Reynolds number is less than about 2,100. Remember, the Reynolds number is dimensionless. Laminar flow gets its name from the word laminates or layers, as all fluid particles in laminar flow move in parallel paths to the overall flow direction, such as shown on this slide. Even though the flow layers are the same, the velocity profile is parabolic. This is due to the fluid particles near the walls moving slower than the fluid particles at the center of the conduit. Think about this. If we have friction dragging on a fluid particle that's touching the wall of the pipe, that fluid particle is going to move at a slower velocity. Then the particle next to it is going to move at a slightly faster velocity, and so forth until you get to the point that's the furthest away from the pipe, which is the center of the pipe. And the particle that is right at the center of the pipe is the one that's going to be moving the fastest. For laminar flow, the average velocity is used in calculations, and that is a number that is typically reported. Now, this concept of the change in velocity in laminar flow only needs to be known as theoretical, as in practice, it is the average velocity that is used and that is assumed as almost being as a constant velocity through the entire pipe. Keep in mind that this is an average velocity, so you may be tested on the P exam on this concept, that the velocity changes through the profile. Now, turbulent flow. Turbulent flow has a Reynolds number greater than 4,000. Remember, the Reynolds number is a dimensionless number. It occurs at higher velocities or with non-streamlined objects. What turbulent flow, it causes flow lines to become chaotic and mixed up. It causes eddies, which are small whirlpools, to form where the flow gets mixed up, as we see here on the slide, and it quickly mixes two fluids together. As a result, the velocity is constant on a turbulent flow because all the particles are hitting each other, so they're all dragged in the same way, so the velocity is constant through the profile. One other key thing when you come into the design of perhaps a treatment system where you need to mix chlorine or alum to precipitate solids. In mixing design, you design a system to have turbulent flow because that is what will allow you to quickly mix two fluids together. It's important for you to have a clear understanding of the differences between laminar and turbulent flow and to recognize the Reynolds number ranges that characterize the two flow types, as those are very common concept type of questions that may be asked in the breadth portion of the Principles of Engineering exam. And this takes us into the concept of friction losses. Where we have pipe with frictions, the energy grade line slopes down rather than being constant or horizontal. We had a bit of a discussion about this during our first recording, so if you'd like to refresh a little bit on this notion, please, you're encouraged to rewatch that portion of the first recording of the hydraulics and hydrology lesson. The difference in elevation between inlet and exit flows is the friction head loss. So friction loss is caused by the roughness of the material of the pipe wall or the roughness of the material of the channel. And that takes us to the concept of relative roughness. Pipes with rough inside surfaces experience greater friction losses than smoother pipes. A specific roughness measures the average size of imperfections inside the pipe. The relative roughness is the ratio of the specific roughness to the pipe diameter. There's a key difference between a specific roughness and relative roughness. The specific roughness is the roughness of the material. The relative roughness is the roughness of the material weighted to the diameter of the pipe. So you may have pipes that have a high specific roughness and a small diameter, and then you have pipes that have a low specific roughness and a wider diameter. And we'll see on the next slide what impact that makes. Now here we see table 17.2 of CERM, which gives us the values for a specific roughness for common pipe materials. As we can see, smooth pipes such as plastic, PVC, or ABS pipes have very small specific roughness values, whether rough pipes such as concrete pipes have a high value of a specific roughness. Table 17.2 lists these values of a specific roughness for common pipe materials. The table clearly shows the significant difference in roughness and, hint, friction loss between various pipe materials. This is one reason why PVC pipes may be preferred over concrete pipes for certain applications. For example, on a water distribution system that has small diameters, a PVC pipe may be preferred over a concrete pipe because there will be a less loss of energy due to friction. Now, there's a key difference between how we calculate a specific roughness and relative roughness. So let's consider an example, or let's say of two pipes. We have two pipes, a concrete pipe that has a diameter of inches, and then we have a steel pipe that has a diameter of 1 inch. Let's calculate the relative roughness for both pipes and see how that differs. So let's start with the concrete pipe. The concrete pipe has a specific roughness So we have a 24-inch diameter concrete pipe. The relative roughness is going to be equal to the specific roughness, which is 0.004 feet, over the diameter of the pipe. So 24 inches is 2 feet in diameter. And that equals 0.002 feet. That is the relative roughness of a 24-inch diameter concrete pipe. Now, let's look at a 1-inch diameter steel pipe. The specific roughness of a steel pipe is equal to 0.0002 feet. And the diameter is 1 inch. So we're going to divide 1 inch over 12 feet so we can get that dimension in feet. So our relative roughness of our 1-inch steel pipe is equal to 0.0024 feet. Based on this calculation, we can show that the 1-inch steel pipe is 20% rougher than the 24-inch concrete pipe. And the reason why is because the diameter is smaller. So there's more friction acting on the fluid. Whereas a 24-inch diameter pipe is bigger. So the friction can dissipate over that larger area. So we can see, even though a steel pipe has 2 orders of magnitude less of a specific roughness when compared to a concrete pipe, when we calculate based on the diameters of these 2 pipes, still the concrete pipe becomes the one that's the least rough when we use the concept of relative roughness. So you can be asked a simple calculation just like this one in the test, in the Principles of Engineering exam, or you can be asked a theoretical question based on this overall concept. Now let's look at friction factors. And let's start with the Darcy friction factor, which is known as F. This is a parameter used to calculate the friction loss in a closed conduit. And the Darcy friction factor is based on the roughness of the conduit and the Reynolds number of the flowing fluid. The Darcy friction factor, it is not dependent on the material of the pipe. However, it is affected by the roughness of the pipe. This friction factor is in essence a reflection of the roughness of the pipe. So for a given Reynolds number, F is the same for any type of pipe material, whether that is glass, plastic, or copper, as long as the pipe material has the same relative roughness. The Darcy friction factor focuses on the relative roughness. Another key concept, the Darcy friction factor does not consider the specific roughness, does not consider the material of the pipe per se. It focuses on the relative roughness of the pipe. Now, the Darcy friction factor is a very easy calculation when we are operating under laminar flow conditions. The Darcy friction factor for laminar flow conditions can be approximated by equation 17.16, which simply divides 64 over the Reynolds number. Equation 17.16 shows this approximate relationship between the friction factor and the Reynolds number. Now, the friction factor is dependent on the pipe roughness and the Reynolds number of the flow, as shown in figure 17.3. The higher the Reynolds number, the less dependent it is on the friction factor. Table 17.3 of CERM gives some variations on equation 17.16 for various pipe shapes under laminar flow conditions. For closed conduits, circular pipes are the most common type of facility. Here we see table 17.3 of CERM. Note how we have the calculation of the friction factor based on different types of pipe geometry. And this is only for laminar flow. Let me highlight that. Only applicable for laminar flow. Look at the different friction factor equations based on a circular pipe, a rectangular pipe, an elliptical pipe. And there are more geometrical shapes further down in the table. So this might be something you would like to tab for the Principles of Engineering exam, for the breadth portion of the exam. I'll say it's not that likely that you will be tested on a pressure conduit that is not a circular pipe, but you might. It is possible. And this table provides you that information. So we looked at the friction factor for laminar flow. Now let's look at the Darcy friction factor for turbulent flow. The equations shown here are only two examples of many that are used to solve for the friction factor under turbulent flow, which can typically be an iterative problem. Equation 17.20 is also known as the Colebrook equation and is the most commonly used equation. Equation 17.21 is the Swamy-Jain equation, which produces some relatively accurate results which are within 1% of the target. This equation is an explicit approximation of the Darcy friction factor. Again, for turbulent flow, the friction factor becomes more dependent on the roughness of the pipe and less dependent on the Reynolds number. In addition to these equations for both laminar and turbulent flow, there's a diagram or a nomograph that you can use to solve for the Darcy friction factor for circular pipes, and that is known as the Moody friction factor chart or the Moody chart, which is a graphical tool that you can use to find the friction factor. And you will see the figure 17.4 of CERN. And this shows that the friction factor becomes constant after a certain value of the Reynolds number, especially for rougher pipes. The Moody chart is a more detailed version of the simple friction factor chart given in figure 17.3, which we saw a few slides before, and is a commonly used method to look up the Darcy friction factor of a pipe. The Moody chart is used by finding first the number on the bottom of the chart and then moving up the curve that represents the relative roughness of the pipe to find the corresponding friction factor. So let me zoom in to highlight how to use the Moody chart to find the Darcy friction factor for turbulent flow. There we go. So how do we use this chart? First, we find the Reynolds number. So let's say our Reynolds number for our flow being studied is 2 million. And our relative roughness for this pipe is 0.004. So once we hit that line, then we go to the left of the chart and we find our friction factor. And that is somewhere between 0.025 and 0.03. So we count the guidelines, that's about 0.028. So our friction factor for a pipe that has, for a flow that has a Reynolds number of 2 million and a pipe that has a relative roughness of 0.004, our Darcy friction factor is going to be 0.028. Now you can see here on this chart, you can also use it to find the friction factor for laminar flow. So let's say our pipe has a Reynolds number of 1000 and it has a relative roughness of, we don't need to use the relative roughness. If we're on laminar flow, we do not need to use the relative roughness. We simply go up until we hit our laminar flow line. So what we find there is that our friction factor is going to be equal to 0.065. Now, the Moody friction factor chart is used for circular pipes, or these are the most common shape for pressure conduits. Now, if you encounter a non-circular pipe on the exam, you may use the equations shown on the table that we saw a little bit earlier for CERM for laminar flow. And you can use the Moody chart if you have turbulent flow to approximate the friction factor in a non-circular channel or non-circular pipe. You can use it to approximate and it can help you solve that problem. So now we've gone through a detailed explanation on the Darcy friction factor. So how do we use that to calculate the energy loss? And that comes to our Darcy equation for laminar flow, which we see here on this slide. Here's the head loss due to friction using the Darcy equation for laminar flow. We see our friction factor, we see the length of the flow, the velocity of the flow, the diameter of the pipe, and the gravitational acceleration. The purpose of estimating the friction factor is so that we can calculate the head loss in pipes. The friction factor may need to be recalculated after finding the head loss in the pipe. The head loss can be added into the Bernoulli equation to calculate how the friction is impacting the velocity, pressure, or elevation of a system. This is very important in pipe network design because the friction in the pipe can impact the total energy needed to get the fluid from the inlet to the various outlets. Now, we also have Darcy's equation for turbulent flow, which we see here on this slide. This method, and we also have Hayes-Williams equation for calculating the energy loss due to friction. Now, Darcy wasteback is used for fluids that have a high viscosity, which are non-watery type of fluids. The Hayes-Williams equation is a good approximation for fluids that have a very low viscosity, such as watery fluids, which for water resources, the Hayes-Williams equation is typically used preferably over the Darcy wasteback equation, because in water resources, we use fluids that are very, very close to water or are just simply water. In water distribution systems, it's water. In sanitary sewer, the sanitary sewer or the sewage is very, very close to water. However, in other engineering applications, such as the oil and gas industry, where we have more viscous fluids, such as oil, the Darcy wasteback equation is used. Now, Hayes-Williams is an empirical equation, and it's one of those equations where we need to be very careful on the units that are requested to be used in the equation. Let me zoom in so you can see that in more detail. Note here, equation 17.29 gives us two options of a Hayes-Williams type of equation. The first thing that we know that changes is the coefficient, this correction coefficient. The second thing that we notice is each one of the variables have a specific required unit that needs to be used. Velocity needs to be in feet per second. Length needs to be in feet, and diameter needs to be in feet for this equation to be applicable. For the second equation, the length needs to be in feet, the flow needs to be in gallons per minute, and the diameter needs to be in inches. There are many other forms of the Hayes-Williams equation, using metric units, using different measures for different units for velocity, different units for flow. So you may find that you have textbooks that have different forms of the Hayes-Williams equation than the two shown here on this slide. While you're practicing for the exam with other friends or colleagues, you may see that their different textbook may have a different definition of the Hayes-Williams equation. The Hayes-Williams equation is still the same, just that note that the difference will be on the units required to be used to solve this empirical equation and the correction factor used. Now note how in these two equations the correction factor changes from 10.44 to 3.022. Now, the Hayes and Williams equation used something similar to the friction factor used on the Darcy equation. However, for the Hayes and Williams equation, it's called the roughness coefficient. And the roughness coefficient is entirely based on the material type. For Hayes and Williams, you don't need to use the concept of relative roughness. For Hayes and Williams, you simply use the material of the pipe. Appendix 17A of SERM shows different roughness coefficients for different pipe materials. Appendix 17A of SERM shows different Hayes and Williams coefficients for different pipe materials. So that's an appendix you're going to want to tab for use in the PE exam and also for when you practice for the exam. Now let's look at pipe systems in series. And let me fit the page so we can see the entire slide. Now piping in series is when pipes are connected from one end to the other. So the ending of one pipe segment needs to be to the starting of the next pipe segment. In piping in series, the flow discharge is constant through all the segments of the pipe. That is our continuity principle. And the loss in each pipe is added up. Piping in series or parallel is similar to a series of springs when they're evaluated whether they're in series or parallel configurations. And the friction loss can be calculated using either the Darcy, Weisbach, or the Hayes and Williams equation. Now here we see some equations that we can use to evaluate for pipe systems that are in series. If the pipe velocity and the flow rate is initially known, the friction losses can be easily found. If they are not known, then the problem becomes iterative. If you review section 17.28 of SERM, you will see how this applies. You can see that the head of a pipe in series is equal to the velocity head plus the head loss due to friction. And the head loss due to friction is going to be equal to your major losses and your minor losses. One other key point is your continuity equation. The flow at point A needs to equal the flow at point B. Now let's see how a system in parallel functions. Head loss in a parallel system is the same for all of the pipes that are running in parallel. And to keep our continuity principle, the flow discharge needs to be equal both at the entrance and at the exit system. So what that means is that our flow is equal to the sum of the flows within each pipe in parallel. So the flows within each pipe in parallel may be different, but their addition is going to be the same as the flow entering and exiting the system. Parallel pipe systems of more than two pipes can be solved using the steps presented in SERM chapter 18.29. Pipe networks can contain both pipes in series and parallel. And these pipe networks that have a combination of the two systems are typically solved either using calculation spreadsheets or specialized computer programs such as the Environmental Protection Agency's software called EPANET. To solve a parallel pipe system with only two parallel pipes, you have to simultaneously solve equation 17.98 and equation 17,100. Solving a pipe network is outside of the scope of the exam due to the complexity of solving one by hand. However, an exam problem may include parts of a very simple pipe network with a pipe consisting of two different sized pipes, or with a parallel system similar to the one shown in the previous figure. To solve a pipe network like this by hand, first solve for the inside One of the ways to measure parameters within the pressurized conduit is the use of different gauges. One of the most common ones used is the pitot static gauge. The pitot static gauge is used to determine flow velocity. Piezometer tubes and wall tap static pressure energy or the hydraulic grade line. Pitot tubes measure the total energy grade line. The difference between the wall tap height, which is shown here, and the pitot tube height is the velocity head. Keep in mind that the wall tap is not facing the flow, so the velocity is not affecting the water head. However, the pitot tube is facing the flow and is facing the center of the flow. So the water head is essentially dependent on the speed of the flow. The wall tap and the pitot tube can be connected with a fluid on the inside of the tubes, also known as a pitot static gauge. This makes the pitot tube dependent on the fluid densities of the flowing fluid and the fluid in the gauge. A common fluid used is mercury. Corrections can be made to the pitot tube gauge to correct for geometric errors and pipe inefficiency. The actual velocity in the pipe will depend on the location of the pitot tube end in the fluid stream. So if we're near the end of the pipe or near the middle of the pipe, because we know that the velocity changes in laminar flow. So let's look at the equations used in the pitot static gauge. The pitot tube is a direct application of Bernoulli's equation. Equation 17.142, which is shown in SI and US units, is derived from Bernoulli's equation. Equation 17.143 can be calculated using the relationship between the energy equation and the pressure head equation. Pitot tubes are used in airplanes to determine both airspeed and altitude, which demonstrates that Bernoulli's equation is applicable in many different aspects of fluid dynamics. So now it's time to review an example problem. So let's go through the problem prompt. During peak conditions, an 8-inch water supply pipeline provides 400 gallons per minute at the end of the line. The total length is 10,000 feet. The hydraulic grade line has an elevation of 350 feet at the beginning and 250 feet at the end. The Hazen-Williams coefficient is 200. What is the pressure head at the end of the line? This problem is another application of Bernoulli's equation. The intent of the problem is to show how to use friction losses when calculating the energy at different points in the system. Please note that both the energy grade line and the hydraulic grade line can be used on this type of problem to graphically picture what is going on. You should be keen in identifying what energy components, is it pressure, velocity, or elevation, are acting at both ends of the water pipe. Then based on that, calculate the friction losses. And finally, you are ready to then solve Bernoulli's equation for the unknown value. Remember, that the change in the hydraulic grade line is the velocity head. Water supply lines run under pressure. So this is a pressure conduit problem. However, because no pressure information is given, it can be assumed that the pressure head is constant throughout the system. This is the first assumption that needs to be made. It is easiest to assume that the pressure head is zero. Because we're not given the pressure, it is okay to assume that the pressure head is constant throughout the system. So starting with that, let's first calculate what is the head loss due to friction using the Hazen-Williams equation. Here we see another form of the Hazen-Williams equation. Note the different conversion factor, where we use length, flow, the roughness coefficient, and the diameter. The diameter is measured in feet. The flow is used in cubic feet per second. And the length is used in feet. Note the different correction factor. So our head loss due to friction comes out to be 15 feet. Because the flow is used in feet per second, cubic feet per second, we need to convert our gallons per minute to cubic feet per second. Because our diameter is used in feet, we need to convert the 8 inches of the pipe into feet. And then the length is in feet, so there's no conversion. What you see here is the use of the roughness coefficient given in the problem as 200. And then we multiply by the correction factor, so we get a head loss due to friction of 15 feet. So since the pressure is the same within the system, because it's not given, we can simply remove these components from the equation because we're going to cancel each other out. Now here the problem uses an assumed pressure of 0. Instead of assuming a pressure of 0, rather just remove them from the equation because they're going to cancel out if they're the same. So we're living with the elevation of 350 feet at the beginning, 250 feet at the end, and the only difference is the head loss due to friction. So what we find is that the pressure head at the end of the line is equal to the change in elevation minus the head loss. So we have 350 minus 250 feet is 100 feet. But we have a loss due to friction, and that's 15 feet. So the pressure head at the end of the line is going to be equal to 85 feet. And that takes us to our second concept